So I'm back after about a month of sitting in the corner of the room taking notes, and I've been asked to talk about a few topics that are special. They're also important for atomic force microscopy. And I'm going to start today with this frequency modulated AFM. And I'll spend about 2 or 3 lectures on that. And we'll then talk about electrostatic force microscopy and magnetic force microscopy, because that's also a technique that's often used by many of you in your research. I thought it would be a good idea to try to provide a summary of where we have been for the past 2.5 months. And that summary is indicated on this slide right here. Very early on, we started to talk about scanning tunneling microscopy, and we gave a brief overview of what STM was. It's a technique that's not widely used because it's best practiced under ultra-high vacuum conditions. The majority of you are taking this class to learn more about atomic force microscopy, and what we have done in the past 15 or so lectures is we have covered both contact mode and dynamic mode atomic force microscopy. And by now you should all understand that either of these two techniques, contact or dynamic mode AFM, both of these techniques require a pretty sophisticated understanding of what's going on if you really want to quantitatively interpret the images and the data that you obtain. That was the main point of the past 15 lectures, is to try to provide you with some physical basis for interpreting the data that you get when you do contact and dynamic mode AFM. So these commercial systems allow you to push buttons and click mouse buttons and get images, but the acquisition of those images does not necessarily mean that you understand the physical process that's going on when you take the image. And so part of the reason this course is offered is to try to provide you with a better understanding of those physical processes. Now, this dynamic mode AFM is really split. If you look at the history of the atomic force microscopy, the dynamic AFM is really split into 2 different camps. Historically, this is what's happened. Up until now, we have focused on this amplitude modulated AFM. The amplitude modulated AFM allows you to obtain an image of a substrate by keeping the amplitude of the cantilever constant as you scan the substrate beneath the cantilever, right? So you focus on the amplitude and you oscillate the cantilever through a large amplitude, and you do this for a number of reasons, right? One reason you oscillate the amplitude of the cantilever, one reason why you cause a cantilever to oscillate is because you want to eliminate lateral forces as you move the substrate from one point to another. If the tip is always in contact with the substrate, right, the tip will literally push things out of the way as the substrate is rastered beneath the tip. This amplitude modulated AFM prevents that from happening. So if you're looking at weakly adsorbed species on a substrate, the dynamic amplitude modulated AFM has all kinds of advantages. In addition, the amplitude modulated AFM allows you to image in 2 different regimes. One is an attractive regime and the other is in a repulsive regime. And we have discussed that many, many times over the last 2 months, the difference between these 2 different regimes of imaging. The price you pay for doing amplitude modulated AFM is there are a lot of parameters that you have to control. And this Veda software has been designed to allow you to appreciate all the parameters that you may not be aware of when you do an experiment, but you should probably be aware of when you're trying to interpret your experimental data. So Veda is a great tool for sorting out all these important variables, parameters that go into understanding an amplitude modulated AFM experiment. So I like to refer to this amplitude modulated AFM as like an industrial strength AFM, because that's the most common method that everyone uses when they try to obtain images using atomic force microscopy. I think by far that is the dominant technique in use around the world today. But there's an alternative way to do dynamic AFM. And that alternative method is to focus on the frequency of the cantilever as it oscillates rather than on the amplitude. Okay? And this other mode of AFM, the so-called FM AFM, which is a frequency modulated mode of acquiring images, this has been called in the community the non-contact AFM, right? To distinguish it from the constant amplitude intermittent contact AFM used when you focus on the amplitude. So this split in the AFM community occurred roughly 12, 13 years ago. And if you watch how the conferences are organized throughout the world, there will be AFM conferences, and usually people that go to those are the people that are doing intermittent contact AFM. And then there are alternative conferences, which also are about AFM, but they're about this so-called non-contact AFM, where you focus on frequency of the cantilever rather than the amplitude. And if you try to get an overview of the two different communities, I think what you'll find is that the FM AFM community tends to be more academic. It tends to be more in physics departments than in materials science and engineering. And it also requires ultra-high vacuum, by and large. Now that story is starting to change slowly, right? You're starting to find companies that implement FM, AFM in their software and in their hardware. But up until a few years ago, the FM, AFM community was basically academic, and it was basically designed at trying to achieve atomic resolution of substrates with AFM technology. Okay? So, what I'm going to talk about for the next couple days is this, or next couple lectures is this FM, AFM, and try to give you some insight into how those experiments work, right? Because it's kind of interesting. It's a different mindset than AM, AFM, in my opinion. So, this is the standard plot that you've seen many times before. It shows a cantilever. That cantilever is positioned at some distance D above the substrate. That distance D is then modified by the turning on of the tip sample forces. So if there's no interaction between the tip and the substrate, you can position the tip at a particular distance above the substrate and it'll stay there. But when you suddenly turn on this tip sample interaction force, which is a combination of DMT and van der Waals, right? The tip bends towards the substrate by a small amount delta. How much it bends depends on the spring constant of the cantilever, and it depends on the magnitude of that tip sample interaction force. Right? So it's a complicated nonlinear interaction, which I think there was a homework problem that asked you to look into that in a little bit more detail. Up until now, the the cantilever was oscillated by some amplitude A0. That's the free amplitude when the tip is far from the substrate. As the tip approaches the substrate, that amplitude A0 was modified, and you use that modification to map out surface topography of a substrate. Today, and in the next two lectures, instead of focusing on A0, we're going to focus on the frequency omega that cantilever oscillates, and we're going to start to ask questions about how the frequency of oscillation changes as you bring the cantilever close to the substrate. Right? And in the process of doing that, okay, what we're going to learn is we're going to learn that you can map out with very high precision the tip sample force as a function of tip sample separation. Right? We'll be able to actually map that out just by measuring frequency shifts in the cantilever as the substrate is allowed to approach the cantilever. So that's the big picture, that's the outline. I thought what we would do is we would start with some real simple problems. And with all apologies to the mechanical engineers in the audience who probably understand this oscillation business very well, I thought I'd still go over it and review it because there's a lot of students in the audience who haven't studied this oscillation frequency and thought about it in any great detail, maybe since you took your introductory course in mechanics. Okay, so I'm going to review about 5 situations, and I'm slowly going to work up to the nonlinear interaction force between the tip and the sample. That's going to be the end of the lecture. But I'm going to start with things that, in principle, you all should understand. And the simplest case is the case of a particle that oscillates in a harmonic well. A harmonic well is a well that's defined such that its potential energy increases as z squared, where z is the displacement of the particle from its equilibrium position. So if the particle is in equilibrium, let's say at z equal to 0, right, I can displace the particle, right, and in the process of displacing it, I'm storing some energy in the system. And what I can then do is I can release the particle, right? By releasing, I just let him oscillate, and he will oscillate back and forth in that potential well. I'm assuming that there is no loss, there's no energy loss in this problem. And the simple question is, what's the frequency at which that particle oscillates back and forth? Right? How do you determine that frequency? So that's the first topic. So before we talk about the frequency, I want to again emphasize that these cantilevers, although they're only a few hundred microns long, when you displace them from their equilibrium position, you can store quite a bit of energy in those cantilevers. And the amount of energy you store is clearly dependent on how far you displace it from equilibrium. So what I've drawn on this slide is just a simple plot to remind you that the amount of energy stored in these microcantilevers can be on the order of hundreds to thousands of electron volts, depending on the spring constant of the cantilever. So if you just displace the cantilever by, let's say, 10 nanometers from its equilibrium position, and if the spring constant of the cantilever is on the order of 25 newtons per meter, right, a very simple 1/2 kx squared kz squared calculation shows you that you can store on the order of 10,000 electron volts in that cantilever. And that 10,000 electron volts of energy can then be imparted to the substrate and cause catastrophic consequences, right? It can be disastrous. On the other hand, if you have a very soft cantilever, something on the order of 0.05 newtons per meter, and you displace it by 10 nanometers, the amount of energy stored is still significant. It's about 50 electron volts, right? But that amount of energy is significantly smaller than the amount of energy stored in these real stiff cantilevers. So when we talk about measuring the frequency of oscillation of the cantilever, right, we want to be conscious of the fact that the displacement of the cantilever from its equilibrium position should be kept to a minimum. Right? You don't want to cause huge displacements of the cantilever from its equilibrium position. If you do, right, you run the risk of having a hammer that's going to be pounding on your substrate. And if your substrate is a soft biological material, right, that hammer could drastically destroy the very, very material you're trying to image. So back to the frequency question. When you have a quadratic potential, the motion in that quadratic potential is referred to as a simple harmonic oscillator. And the simple harmonic oscillator is really simple, right? This is a problem that all of you have learned to solve in your introductory physics course. The equation of motion is basically gotten from Newton's law of motion. You say the force F equals ma is equal to minus the derivative of that interaction energy, that energy potential, 1/2 k1z squared. And that allows you to write an equation of motion which has a sinusoidal solution. So z depends on z, the form of the solution for z has to be either sine or cosine depending on the initial conditions of the problem. And I think all of you know from the earlier lectures that the frequency of oscillation back and forth in that well is just proportional to the square root of the spring constant K divided by the mass of the particle that oscillates in that well, right? You can define another parameter called the period of oscillation. That's the amount of time it takes for the particle or for the cantilever to go through one complete cycle of motion. That period of oscillation is referred to as capital T, and it's defined to be 1 over the frequency F. So if you measure the frequency of oscillation of your cantilever, the time it takes to undergo one complete cycle of oscillation is just 1 over that frequency. So these are important parameters that we need to keep track of, right? I like to talk about conservation of energy in this system because there's no energy loss. And the way you conserve energy is you set the kinetic energy plus the potential energy. You add those two up. And since the velocity of the particle, dz dt, depends on its position in that well, and since the potential energy stored in the system also depends on the position of that particle in the well, right? You've got this trade-off between potential and kinetic energy, right, for energy to be conserved. And so that's the first equation on this slide. It's just a conservation of energy statement. The total energy stored is given by the displacement of the particle, the initial displacement of the particle, and it's indicated by that dashed horizontal line called E total. From that equation, that first equation, you can actually solve for the velocity of the particle. dz dt is a function of position z. And in particular, you can start to ask questions about the time that the particle spends at different points as it oscillates back and forth across that well. So that's the equation I label 1, right? You can formally take the second equation on that slide. You can solve for the time. And the time is an integral over position dz divided by that square root function that I've got in blue. Okay? And so you can start to ask the question, you know, from an energy conservation viewpoint, you can start to ask the question, what is the period of oscillation of the particle in this well? Or what is the oscillation period of the cantilever? Cantilever oscillates in a quadratic well. And you can solve that problem by specifying the form of the potential well, V of Z. In this case, V of Z is 1/2 K1Z squared. It's the red term. You just drop that into the denominator of equation 1. Right? K1 is some number that you know. And you can then integrate, for instance, from t equals 0 to t by 4, which is 1/4 the period of the oscillation, right? And in that 1/4 the period of the oscillation, the particle will oscillate from its position at the bottom of the well all the way up to this position called Z max, right? And when it gets to position Z max, that's 1/4 the total period, you know, so you can solve that equation, right? That turns out to be an integral that you can look up in an integral table. Comes out to be an arc sine function. You have to evaluate the arc sine function at the two limits of the integral. And at the end of the day, what you find is you find out that that period, 1/4 the period, t by 4, is just equal to this quantity square root of m over k times pi over 2. And since that's 1/4 the total time it takes for the particle to oscillate, you have to multiply that quantity by 4 to get the period. When you do that, right, you get the simple result that we got when we solved the differential equation to begin with. Now, the advantage of this approach, you say, well, why do you go through all this trouble, right? Because you can just solve the differential equation straight off, right? Well, the reason you go through all this trouble is because it gives you some insight into the situation when the potential well starts to become distorted, when it's no longer quadratic. And certainly the well that the cantilever oscillates in is very far from quadratic, right? It's got this very repulsive term. It's got this van der Waals interaction. So what we're trying to do is we're trying to develop a technique that we can apply to these very simple problems, but that's general enough that we can translate it and we can apply it to more and more complicated potential wells to try to get some insight into how the frequencies are going to shift when the cantilever oscillates in wells that are not quadratic. So that's the plan, right? Now, the great thing about this simple harmonic oscillator is that the frequency f that comes out of this analysis in no way depends on Z max, right? So you can make Z max whatever you want if there's no energy loss, right? The particle will still oscillate at the same frequency f, which is the last equation on this slide. And that's a property of a simple harmonic oscillator that you probably all learned about a long time ago, but maybe forgot. It's referred to as an isochronous oscillator, which means that the frequency or the period of oscillation is independent of amplitude. That simple approximation breaks down as soon as we start to change the shape of that harmonic well, as soon as we start to make the harmonic well deviate from a parabolic behavior, that feature of the frequency will change. Okay, we're gonna try to quantify how much the frequency will change and how the change in frequency depends on the shape of the well. That's the big picture. So what you can do with this formalism that's sketched out on the left side of this slide is you can start to ask the question, if you focus on equation 1, you can start to ask the question, how much time does the particle take to be in a position dz at some point in the motion of the particle in this well? And it's basically equating the two integrands on the left and the right side of the equation, of equation 1. So if you tell me where dz is centered on that well, I can evaluate that blue square root, right? And I can divide the value of that square root into dz, and that will tell me the time interval that the particle actually spends as it undergoes this oscillation back and forth. And that's an interesting thing to think about. And I tried to sketch that out a little bit more here on this slide. Again, I have the quadratic potential. I've defined my Z max minus Z max, which tells me the limits of oscillation of the particle in the well. And then I can pick any interval I want, any dz. I indicate dz as a small distance between those two red dashed lines, and I can ask how long does the particle spend in that tiny interval dz. And I do that by going back and I evaluate the integrand in equation 1 on the previous slide, and when I do that, I find a plot that's on the upper right of this view graph, and it shows that if you plot the time, the fraction of the time compared to the total period of oscillation, if you plot that as a function of z over z max, it shows you, not surprisingly, that the particle spends most of its time at the endpoints. Right? You can see the curve peaks up when z over z max is on the order of plus or minus 1. And it's sort of intuitively obvious, because that's when the particle stops, turns around, and starts to roll back down the hill again. So the particle spends most of its time at the endpoints. And so if you're trying to characterize the motion of this particle in this well, and you want to get you want to get it right most of the time, what you tend to do is you tend to focus on where the particle spends most of its time, and that's at the end. So that feature, right, will persist as we move through these different calculations. And when we actually get to the real situation where the cantilever is oscillating in the tip sample force well, right, we're going to find out that the answers we get are always going to be heavily weighted by the endpoints of the oscillation, right? Just as this very simple analytical problem is heavily weighted by the endpoints of the oscillation. That's because that's where the particles, or where the cantilever spends all of its time. The other interesting thing about this quadratic potential is that the spring constant is independent of position, right? And that's obvious to anybody that's solved a simple problem. But if you just define the spring constant in terms of the second derivative of the potential with respect to z, since the potential is quadratic, it's very clear that the spring constant for the simple harmonic oscillator is constant, independent of position. And that's indicated on the bottom right-hand panel of this slide. So these are things that you probably all well know and understand. But it's interesting to me to watch how these simple conclusions change as we start to modify the shape of the potential well. And my feeling is that if you don't understand it for this situation, then you kind of get confused as we start to modify the potential well a little bit. So that's the structure of the remaining part of the lecture. So I'm going to consider 4 cases, and I'm going to try to indicate different ways that you can make the oscillation frequency vary just by changing things with this simple harmonic oscillator model. And probably the simplest way to make the frequency change is to introduce a damping. This again is a problem that if you've taken upper level mechanics, maybe a physics 300 level mechanics course, this feature comes in quite prominently. In this case, what happens is you say when a particle oscillates in the well, it's possible it can lose energy, right? And what happens is that now, because the particle can lose energy, its oscillation damps out, and it eventually settles to the bottom of the well after a certain number of oscillations. And you can define a certain energy loss per cycle, which would then describe quantitatively how many cycles it would take for the particle to settle down, lose all of its energy. So if you lose a little bit of energy per cycle, it'll take many cycles before the particle settles down. If you have a large energy loss per cycle like I've got in this problem, after a few oscillations, the cantilever stops moving. We're not specifying what the loss mechanism is, we're just saying that there is one. So the implications of this model is that a new term has to be included in the differential equation. This new term is now an energy loss term, which is indicated by the red term that's added to the equation. C is a parameter that defines how much energy is lost per cycle of oscillation. Z dot is the velocity of the particle. And if you just follow this equation of motion through, again, this can be solved analytically, what you find out is that the frequency of oscillation in that cantilever shifts ever so slightly just because of the damping mechanism. How much does it shift? Well, it depends on this damping coefficient C squared divided by this 4K1 over M, where K1 is the spring constant of the cantilever. So just by including a damping mechanism, the frequency already starts to shift, right? Frequency already starts to shift. Second case I like to consider is the case of a symmetric oscillator, no damping, but I'm going to make it nonlinear now. The way I'm going to make it nonlinear is I'm going to modify the potential well that the particle or that the cantilever oscillates in. I'm going to add a z to the fourth term, and I'm going to add that in addition to the quadratic term that we've already discussed in some detail. So what is the effect of that 1/4 K3 z to the fourth term? Well, the total potential well that the particle or that the cantilever would oscillate in is now indicated by the red curve on this graph, this view graph. And that 1/4 K3 z to the fourth term just causes the potential well to pinch up a little bit. How much it pinches up depends on the size of that constant K3. So this is known as the hard spring approximation. What happens is the nominal spring constant K1 is now modified by this parameter K3. And the particle now oscillates in a well that's not quite quadratic, right? It's got this, it's got a steeper slope as you get further away from equilibrium position, right? It's symmetric, right? It's symmetric. So everything I'm going to talk about is regarding this symmetric well. So this equation is harder to solve, it turns out. If you try to work it out, you'll find out that the solution actually requires a sum of harmonic terms. The harmonic terms happen to be integer multiples of the resonant frequency omega naught. And from the symmetry of the problem, you can eliminate a lot of the coefficients in this proposed solution. In fact, you can eliminate all the A's, and you can eliminate all the B's that are even. For n equals even, all those B's disappear. And the lowest order term, the leading non-zero order term, would then be just a coefficient B1 times the cosine of omega t. And if you put that back into the differential equation and you work out the solutions, you'll find out that the frequency of a particle or of a cantilever, frequency of a cantilever oscillating in this hard potential well, this hard spring potential well, it acquires some very interesting characteristics that are worth talking about. So the frequency that I get when I work through all this detail is written on the bottom of the slide, and what you'll notice is the first term, the leading order term in the square root, is the K1 over M term that we've already discussed. But there are additional terms that describe the frequency of oscillation, and those additional terms are related to this coefficient B1. And so you can write that the frequency of this oscillator shifts. It shifts from the frequency F naught plus a term delta F that now depends on the amplitude of oscillation of the cantilever. So this is a characteristic problem that occurs. This is a characteristic feature of oscillators that occur when the well is no longer perfectly quadratic. So if you start to modify the well, right, you introduce this new feature. The frequency depends on the amplitude. So if you have a system and you don't know whether it's quadratic or not, right, the way to sort that out is to change the displacement of the system from its equilibrium position, measure its oscillation frequency. If the oscillation frequency is independent of amplitude, of displacement, if it's independent of how far you displace the particle from its equilibrium position, then it's probably quadratic is pretty good approximation. But if the frequency starts to depend on amplitude, then that's clear indication that you've got a nonlinear problem. So you can run through, I just evaluate the frequency shift, for instance. So I arbitrarily picked two parameters, K1 and K3. They're indicated in the upper left-hand side of this graph. All right. I use those parameters to evaluate this term under the square root. And I just want to emphasize the point that if you plot that out as a function of B1, that B1 is now the displacement of the particle from its equilibrium position, is the displacement of the cantilever from its equilibrium position, right? The frequency shift can be quite large. Right? It just depends on the size of the parameters that you choose. And that frequency shift is actually telling us something about the shape of that potential well. And that's ultimately what we're interested in, right? We're not so much interested in the fact that the frequency shifts. It's like, okay, if we can measure the frequency shift, what do we learn about the well that the particle or that the cantilever is oscillating in? So that's the logic of this discussion. And again, you can do the same type of analysis. You can ask, when this particle oscillates in this symmetric potential well with this z to the fourth term, where does it spend most of its time? And you can go back and you can take those formulas from about 4 or 5 slides ago. They still apply because energy is still conserved. And you can start to ask the question, you know, how much time does the particle spend at the endpoints compared to, let's say, time in the middle of the oscillation, in the middle of the well? And again, I worked it out for the parameters I've listed on the previous slide, right? The fraction of time divided by the total period T of oscillation in this well is given in the upper right panel of the slide. And you can see quite nicely that there's a big spike. This is for a 2 nanometer displacement, so I picked B1 of 2 nanometers. That's the maximum displacement. You can see there's a huge spike at the endpoints, which indicates that the particle spends most of its time as it slows down, turns around, and comes back again. Now, the new feature that comes into this problem is that the spring constant is no longer constant independent of position. And that's obvious because if you just take the second derivative, again, this is in the bottom right panel of the slide, if you just take the second derivative of the potential and you call that the spring constant, in contrast to the case when the well was quadratic, right, and spring constant was constant independent of position, now you start to pick up a curvature in that spring constant, right? And it depends. It's not easy to answer the question, what's the effective spring constant of that system? Because the spring constant depends on the position. So how might you answer the question, what is the effective spring constant that's important in this system? You know, that's a fair question to ask. And the one way to think about it is to say, well, why not weight the spring constant as a function of position by the amount of time that the particle is at that position? So if the particle's at the position for a short period of time, then maybe that spring constant at that particular point isn't so important. But if the particle happens to spend most of its time at the endpoints of the oscillation, right? Then maybe we ought to weight the spring constant to reflect that fact, because that's where the particle spends all of its time. So you can make an argument, right? I'm not going to make it quantitatively, but you can make an argument that the effective spring constant of this system should be the spring constant at the ends of the motion, because that's where the particle spends most of its time. Okay? And again, this will come back when we discuss the tip oscillating in the very nonlinear potential well due to van der Waals forces, right? This will come back and this feature will emerge, right? But I just want you to start thinking about these problems and how you might sort them out. The third case I want to discuss is the case of an antisymmetric oscillator with no damping. So now what I'm going to do, right? You say, well, the previous discussion was nice, but it doesn't even come close to resembling the shape of the potential well that the tip oscillates in, because the previous case was symmetric. And when the tip oscillates in the potential well, the potential well is clearly asymmetric, right? It's much steeper when you get closer to the sample than it is when you get far away from the sample. So how can you mimic this asymmetry in the potential well in a simple way, right? How do you understand that? Well, the answer is you put in another term into the model, right? So in this case, you make the well asymmetric, you put in a z cubed term, as I've indicated in the yellow box. And so now the shape of the potential well for this asymmetric case is sketched out by the red curve. And the blue curve on this plot is the case of the symmetric well. And I hope it's obvious now that the well, for the parameters that I've chosen, right, the well starts to resemble, ever so slightly, the potential well that the cantilever oscillates in, because now, as you move towards negative displacements, the well clearly gets steeper, whereas when you move to positive displacements, the well tends to be a little bit shallower, right? So we're trying to work our way up to the real problem of what happens when the tip oscillates in a well determined by the tip sample interaction forces. Well, this is right. This gets more complicated to solve, but basically what happens is, again, the way to solve the problem is you have to say that the displacement is now an infinite sum of sines and cosines. The fact that the well is asymmetric means that you pick up both n even and n odd terms in the solution, right? So the solution of this problem indicates that the particle will start to oscillate at even and odd integer harmonics of the frequency for the symmetric well. And again, you get this interesting behavior that if you just keep the lowest order term, which means set n equal to 1, you pick up this B1 term, right? Now the frequency of oscillation is a little bit more complicated than before. Why is it a little bit more complicated? Because it's got a positive sign for B1 squared, and then it's also got a negative sign for B1 squared. So now, whether the frequency is going to go up or down is going to depend on the relative magnitudes of the coefficients in front of the B1 squared term, right? So it's a little bit more complicated. Again, the frequency depends on amplitude, and these integer harmonic solutions start to come out. So what this tells you is when your tip is oscillating in an asymmetric well, and if you look very closely at the frequency response of the cantilever oscillating, you ought to start seeing integer harmonics that start to appear in the spectrum, right? Just because the well is asymmetric. That's what this model is trying to teach you, right?
Well, I'll just quickly add on that even A0 will depend on B1. It's not a fixed number, it actually depends on the amplitude. If the solution for A0 is also good enough. it's an interesting thing that even the DC component depends on the.
So I guess the point is that as the well starts to become asymmetric, right, the particle can roll away in its equilibrium position from z equal to 0?
Well, I guess the point is that if it's solved for, it turns out the mean position moves over depending on B1. If B1 is 0, it just rolls over just to where the bottom is. But as it oscillates, it drifts away from that position. That's the key. That's another insight that just this Fourier analysis would show.
Yeah, I didn't work out the solution for A0. I was just interested in frequencies. It was hard enough for me to get this.
Well, it simply comes from the z squared term, right? When you put in, if you look at the B1 cosine omega t term, when that gets squared, it's going to be B1 squared cosine squared, which gives
2 omega.
2 omega and a DC term.
Oh, I see.
And that basically comes from the even power terms in the force expansion, or equivalently the odd power term in potential. The one that causes asymmetry is what causes the A0. Because you don't get A0 if it's symmetric potential.
Okay. Any other? Well, just to point out, you can evaluate for the parameters I chose, you can start to evaluate how the frequency depends on the displacement of the oscillator. And the dashed line in this plot indicates the case when the potential is symmetric. When you start to introduce this z cubed term, right, now the amplitude of oscillation for large amplitude oscillations, the frequency actually starts to decrease from what you would expect. So it's a frequency decrease. So the point is, for an asymmetric well, you start to get a frequency decrease as the amplitude of oscillation of the cantilever or the particle in this well gets bigger and bigger. And not surprisingly, right, these are the standard plots that we've already discussed. You can start to ask the question, how much time does the particle spend at different points in the well? And again, it's not surprising that the particle spends most of its times at the end points. If you again try to define a spring constant for this system by just formally defining the spring constant as the second derivative of potential with respect to z, right? Now the spring constant is really funny. It's not even symmetric anymore. And it's a fair question, what spring constant might you use for the system? And again, I would argue that you probably, if you're going to define an effective spring constant, you're probably going to try to weight the spring constant at the ends of the motion, because that's where the particle spends its most time, right? Rather than in the middle of the motion where the particle spends hardly any time at all. Okay? So you get this idea again that the effective spring constant for the system is going to be some weighted average, which takes into account the motion of the particle. So, with all that background, after you've been reminded of all these things that mechanical engineers probably already well understand and know, right? We're back to the problem of the oscillating tip, right? And we're trying to understand now how the frequency of this oscillating tip is going to vary as we move the tip at various positions in this very asymmetric interaction potential well, right? So what I try to do is I'm flipping back and forth between the tip sample force and the tip sample interaction energy in this discussion. Whenever I talk about the tip sample force, I try to use green XY axes. When I'm talking about the interaction potential, I try to use black axes to try to get you to focus on what I'm talking about. But this is the standard problem that's been discussed many times in the class. You have this tip sample force that has this very nonlinear shape. You position the cantilever at some position z, You turn on that interaction force. That interaction force is attractive for large Z, so it causes the cantilever to bend towards the substrate. How much does it bend towards the substrate? Well, it bends by an amount delta. How big is delta? Well, it depends on the spring constant of the cantilever, and it also depends on the strength of the interaction force. So the cantilever will bend such that the restoring force on the cantilever, which is the spring constant of the cantilever times its displacement delta, when that restoring force equals the attractive force at the new position of the cantilever, when those two things balance, as indicated by that static free body diagram, that's going to determine what the new equilibrium position of the cantilever is with respect to the substrate. So when you're far away from the substrate, delta is real small, right? It's not a big deal. But as you get closer and closer and you start to experience the full nonlinear nature of that interaction force, delta can start to become appreciable. It depends clearly on how strong of a cantilever you're using. And now the new feature that we're going to add to this standard problem is we're going to cause the tip, now we're going to impose an oscillatory motion on the tip once the cantilever has achieved its equilibrium position, as indicated by that black dot on that slide. And we're going to ask what the frequency of oscillation of the cantilever is for different values of D star as we systematically move the cantilever from a position far from the substrate, closer and closer to the substrate. We're going to ask the question, how does the frequency of oscillation of that cantilever shift? And the way we're going to answer that question is based on the method that's been laid out in the previous 2 or 3 examples. Right? The problem now is that the shape of the interaction force or the shape of the interaction potential is much more complicated than those simple models that we use to build up some intuition. And not surprisingly, the mathematics to sort out the question of what the frequency is for different values of D star. Not surprisingly, that's more complicated than anything I've done up till now. But that's the scope of the problem. I guess the point I'd like to make is that interaction force between the tip and the substrate is really different. It's not like a conventional spring, right? It's not like a conventional spring at all, and I try to illustrate that schematically in this next diagram, where I first look at the conventional spring case, just to remind you what should happen if you've got springs that you normally deal with in real life. If you have 2 springs, right, K1 and K2, so K1, the spring constant K1 is going to represent the spring constant of, let's say, a cantilever, and K2 is going to represent the interaction force between that mass M and some substrate, right? If you displace the mass M from its equilibrium position by an amount Z, the conventional spring system says that the mass M will feel 2 forces. And those 2 forces will be in the same direction, and they will act to restore the mass M to its original position. Right? So the top spring is pulling the mass up. The bottom spring is pushing the mass up, so F1 and F2 from spring K1 and K2 act in the same direction. You've got a very simple equation of motion. You can solve that equation of motion and you find out what the new frequency of that system is. It turns out it's the square root of the sum of the spring constants, K1 plus K2, divided by the mass of the object. When we deal with the interaction of the tip with respect to the substrate, the spring at the bottom is different because the spring at the bottom is now an attractive spring. So as we displace the tip from its equilibrium position, right, the top spring is now has an effective spring constant which is due to the cantilever. That's going to try to restore the mass to its original position. But the bottom spring is an effective spring constant between the tip and the substrate. And an effective spring constant between the tip and the substrate is such that it tries to pull the tip closer to the substrate. It's an attractive force. So now you've got this situation where the cantilever is pushing one way, the tip sample force is pushing the other. The equation of motion is modified accordingly, right? You've got to put an extra minus sign into the equation of motion. And what happens is the frequency now of that system is different than the frequency for the conventional system. That's the thing you want to take away from this discussion. So this tip sample spring, right? If you try to represent the force between the tip and the sample by a simple spring, which is what experimentalists do all the time. That's about as complicated as we can think, right? The spring that's between the tip and the sample is different. It's got this attractive feature to it, and the end result is that the frequency of that mass M, right, is now downshifted. The resonant frequency of the system is downshifted when the tip interacts with the substrate. So if you're trying to understand what the nature of that force is that's acting between the tip and the substrate, and let's say you don't have any theoretical models to guide you, right? If you're trying to understand how that force varies with position, the simple explanation is measure the resonance frequency of the cantilever at different positions above the substrate. And if you do that, right, you should find a downshift in frequency, in resonant frequency, and the downshift is going to be governed by that effective tip sample spring constant K for different positions that you position the cantilever with respect to the substrate. So it's a real clever experimental way to get at a problem that, experimentalists can't go and measure directly, right? How would you measure that interaction force? You can build models and figure out the consequences of those models, but experimentally, this is a technique that allows you to get at it just by measuring frequency shifts. So the point is the downshift in frequency turns out to be just the ratio of KTS over KC to first order. And so if you know KC and you know what the frequency shift is at some position, then you can work backwards and infer K sub TS. And right, K sub TS is interesting because it's just the slope of the interaction force at the equilibrium position that the cantilever assumes, right? It's that magenta line, which is supposed to be the slope of the interaction force at that particular position, D star. So if you know the slope, that's telling you something about the shape of the force. So it's great. It's really, really a nice idea. So here I just work out, I just put in the arithmetic to calculate what the frequency shift is. I just explicitly calculate omega minus omega naught. And then I use the approximation that the slope, or that the spring constant between the tip and the substrate, between the tip and the sample, I use the approximation that that's just equal to the derivative of the force with respect to position. And what you can then do is you can solve that equation, and you can actually work backwards and get an expression for the force that's acting on the tip at a particular separation, at a particular tip substrate separation. And the force at that particular tip substrate separation D star, which is the equilibrium separation after the tip is moved by the forces acting on it, right? The interesting thing is that force is just the integral of the frequency shift over all Z, right? So you can just do the arithmetic and you can get this very simple formula. The proportionality constant between frequency shift and force is just the spring constant of the cantilever. And so now this is great, right? Because it says if you want to actually map out the force as a function of position, what you have to do is you have to experimentally measure the frequency shift as a function of position and then just do this integral. Right? And if you do this integral, you'll actually back calculate out what the force is versus position. So that's the basic idea, right? That's the motivation behind this non-contact AFM community. These people are very, very interested in mapping out this force as a function of position from experimental results. And the motivation behind that mapping is given by this simple solution that I've outlined here. You can put in some numbers just to make it a little bit more explicit, right? Go back to some of the topics that we discussed earlier in the semester. You can pretend that the tip sample force is dominated by this Hamacher constant, or by this Hamacher force between a sphere and a flat plane. If you go back and look at the lecture notes, right, that tip sample force is proportional to the Hamacher constant h. It's proportional to the tip radius. And this factor of 6 is just from geometry, right? When you track that factor of 6 down, it's just due to the geometry between the sphere and the plane. It turns out it's got a 1 over z squared dependence because you have to integrate the force over the geometry of the tip. So you can, with this model, you can then evaluate what the tip sample spring constant is. It's a simple derivative, and then you can start to calculate what the frequency shift is as a function of the tip sample separation, d star. Right? So again, it's just working out arithmetic and using the results on the previous slide. Notice the frequency shift is negative, which means that as the tip gets closer and closer to the substrate, the frequency shift decreases from the resonance frequency that you would have measured if the tip were far from the substrate. So there's always a frequency decrease. And of course, that's related to the asymmetry nature, the asymmetric nature of the potential well that the tip is oscillating in. How big is the frequency shift? With this model, it clearly depends on the tip radius. It clearly depends on the Hamacher constant. I just ran through some calculations to give you a sense of how big the frequency shift is. And so I picked a 10 nanometer radius tip. I picked a spring constant that's for a cantilever that's 40 newtons per meter. Those are things that you can commercially buy. And what you see is that if the spring constant's on the order of 10 to the minus 19 joules, that's about 1 electron volt, give or take a little bit, right? The frequency shift as a function of position could be on the order of 15%. 15% decrease from its value when the tip was far from the substrate. As the Hamacher constant gets smaller, right, factor of 10, you can see that the frequency shift starts to become on the order of 1% or so. So if you want to implement this technique experimentally, if you really want to know how the tip interacts with the substrate, right, you have to be able to build a system that's capable of measuring frequency shifts that are a few percent or less. Right? If your experiment isn't good enough to measure those frequency shifts less than a few percent, then this technique is not going to work for you. But it turns out, as we'll talk about in the next lecture, that's something that you can easily do. So everything I said up till now for the interaction between the tip and the substrate was based on a small amplitude approximation. I assumed that the amplitude of the tip as it oscillated in the harmonic well of the cantilever was small, but clearly that doesn't have to be the case. You can imagine cranking up the amplitude of the cantilever so that the cantilever now oscillates and feels the full richness of that potential well. And of course, the potential well is going to be modified by the shape of the interaction energy between the tip and the substrate. And I've tried to schematically indicate that in the bottom half of this slide. And if you want to understand how the tip oscillates in this asymmetric well, then you've got to go back and use some of those techniques that we discussed in the first part of the lecture, right? Those techniques are completely general, right? You can do that for this asymmetric well, large amplitudes. I just summarize the results here. You can do it mathematically using those formulas. And again, what you find is not surprisingly, that the time that the cantilever spends at the endpoints the oscillation. That's the dominant contribution to the motion. You can again calculate the effective spring constant by just formally taking the second derivative of the interaction potential. I list the values. I use a combination of van der Waals plus DMT. In this particular example, I just set the tip at a 0.8 nanometer separation from the substrate. Right? And what you see is that the effective spring constant of the system now is really asymmetric. As the tip gets very close into the substrate, the spring constant jumps up by factors of almost 100 compared to what it is when the tip is far away from the substrate. And the interesting thing is, because when the tip is far away from the substrate, the spring constant, the effective spring constant is so small, right, that the effective spring constant for the system starts to be dominated by what happens at the closest approach of the tip to the substrate, right? So if you want to find an effective K for this system, it's going to be heavily weighted towards the values of K when the tip is very close to the substrate as compared to when the tip is very far from the substrate. That's just because of the very asymmetric nature of our definition of K here. So it becomes a question how to measure the tip sample force. How to measure that tip sample force is you systematically vary the position of the tip with respect to the substrate for arbitrary amplitude of oscillation of the tip. Right? That's a very important problem to solve. And it was actually formally worked out by Sater and Jarvis in 2004. They have this very heavily cited paper in which they actually develop accurate formulas that allow you to interpret frequency shifts in terms of tip sample forces. Okay? And I just want to summarize the results of their analysis. I don't pretend to understand the mathematics behind it, but what they tell you is that if you measure the fractional frequency shift, which is a function of capital omega, or which is designated by capital omega in their formula, right? If you measure that frequency shift as a function of position, then what you can do is you can infer the force, the tip sample force, at the minimum position that the tip is above the substrate in the course of an oscillation cycle. And the reason the force you infer is at the minimum point in the cycle is because that's where the tip is basically spending all of its time, right? And their formula has got three terms associated with it. The first term is unity, and it turns out that's just the standard result that you would get for a very small amplitude oscillation. So if the tip amplitude oscillation is very small, then that unity factor is essentially the same factor that I wrote down earlier for small amplitude oscillation. There's another term which is for the large amplitude. So as the amplitude of the tip gets very large, right, the way the tip experiences the interaction force is completely different. Notice you got that square root of a quantity that can go to zero. That's very similar to the expression that we had for the kinetic energy of the tip that we started off with back at the beginning of the lecture. And then there's an interpolation term, right? There's an interpolation term that allows you to go from the small amplitude to the large amplitude case. And so using this formula, the bottom line is, the take-home message is that if you can measure the frequency shift as a function of position, and you put that information into this formula, and if you know the amplitude oscillation of the tip, and if you know the spring constant of your cantilever, then you can infer you can actually map out experimentally the force as a function of position, just by measuring a frequency shift. So that's really a cool thought, cool idea. And if you come back next Tuesday, we'll explore that thought in a little bit more detail. But I have to quit today because I'm a couple minutes over. So Maybe I can take questions offline as we wait for the next class to come into the room. So, thanks.